So here the today's topic is, that is packing of, let us go for packing of crystals. If you go for packing of crystals here, that is what is the necessity for the spheres or the atoms or ions to undergo certain kind of packing. So actually what is happening here is, that is tight arrangement of the spheres. These spheres can be atoms or ions or molecules, whatever. The tight arrangement of atoms or ions which occupies maximum space, maximum availability of the space within the crystal lattice, such that you find that the density of crystal is maximum. This is the purpose of the packing of crystals. That means they occupy the maximum amount of space, and thereby that results in the maximum amount of density present in the given crystal lattice. So here in the packing of crystals, here we have to discuss under three different broad categories. That is, here we have types of packing of crystals, packing of crystals. In this we have three types. One is one dimension packing. Second is two-dimension packing, and the third is, that is three-dimension packing. If you go for one-dimension packing, in one-dimension packing, what we are noticing is, you just take some group of cricket balls, or you take some marbles or cricket balls, and these cricket balls in a given plane, in a horizontal plane, you just try to place them one besides the other. So when you are trying to place one besides the other, you find that these spheres are usually spherical in shape, so they come in contact like this. It is a single layered pattern of arrangement. It's a single layered pattern of arrangement of spheres. You find that here, if you take one reference sphere, suppose if this is the reference sphere, I am just marking that sphere with a cross. If this is the reference sphere, you find that the two adjacent spheres, this is one sphere which is coming in contact, and this is another sphere coming in contact, and this is the sphere in choice, that is reference sphere. The two other spheres are trying to come in contact. You take any other, suppose if you are taking this as reference sphere, then this is going to become 1 and this is going to become 2. That means here very clearly we are able to understand that in one dimension packing, because all the spheres are of the similar type, so the packing is of the type A of A type of arrangement. A of A type of arrangement. If you consider each sphere as A, only one type of spheres are present in one dimension packing. That's why we can say A of A type of packing, and here the coordination number of the one dimension packing is always 2, because you can see that for a given reference sphere, the two spheres are coming in contact. This is reference sphere and this is reference sphere. For these two reference spheres, the two spheres are coming in contact, so therefore the coordination number of the given sphere in one dimension packing is always equal to 2. Now after one dimension packing, go for two-dimensional packing. In two-dimensional packing, we have two different types of packings here. One is, you can take square close packed packing, and the one is that is hexagonal close packing, HCP. Here square close packing SCP is called square close packing, and HCP is hexagonal close packing, and HCP is hexagonal close packing. So what we are noticing here in the case of the SCP and HCP, what is the difference between SCP and HCP? So if you draw the diagram, if you take the three-dimensional diagram of the SCP and HCP, then we will come to know what kind of arrangement, what kind of tight packing of the spheres is taking place from one layer to another layer. Just by taking the 3D diagrams of both the SCP and HCP, we can understand what kind of packing is taking place, and we'll try to learn about that. So here in the two-dimensional packing, that is SCP of two-dimensional packing, I'll put it in this way, and what we can do here is you just take a layer. Suppose you are just starting with one layer. In the first layer, you are finding that all the spheres, they are coming in contact like this. This is the first layer spheres, all of them they are coming in contact. In the second layer, what is happening? I am trying to superpose the second layer spheres with the first layer spheres like this. Actually, there are no gaps here. There should not be any gaps. So you can find that completely packed. You can find that they are simply superposed. So here also a kind of superposition is taking place, one sphere over the other. What we are noticing here is all of them, suppose if this is the first sphere, this is the first layer, this is the first layer, then this will be the second layer, then this is third layer. So what you are noticing here is like if you are just, suppose if you take a vertical plane like this is the vertical plane, all the spheres are one above the other, they are trying to superpose, and in the horizontal plane also you can find that all of them, they are in the same plane. So that means whatever may be the number of layers, we are not able to differentiate the first layer from that of the second layer. So all the layers are almost, they are trying to get arranged themselves in the regular pattern by superposing one over the other. That means we are making sure that the second layer spheres are placed at the head of the first layer spheres. We are not trying to change the plane of the position of the spheres. All the spheres are in the same plane. So if all the spheres are in the same plane, like vertical plane and horizontal plane, if you are trying to make a comparison, it's very clear that we are trying to superpose the second layer spheres with that of the first layer and third layer spheres with that of the second layer. If that is the case, so therefore what we have to understand here is, suppose if I am taking one reference sphere here, in the middle layer I am trying to take one reference sphere, then you can find out how many spheres are actually coming in contact with the reference sphere. If this is the reference sphere, then the number of spheres coming in contact are 1, 2, 3 and this is 4. So 4 spheres are coming in contact. So therefore the square close packed of two-dimensional packing, the coordination number is always 4, because the number of spheres coming in contact with the reference sphere is equal to 4. So therefore outright we can say that in two-dimensional packing the square close packing coordination number is equal to 4. Now go for the next case. If you go for the next case, that is hexagonal close packing of two-dimensional packing, close packed of two-dimensional packing of crystals packing. So here what we are noticing here is, like you take a layer, and here one more thing, you are finding that the first layer is of the A type, second layer is of the A type, and third layer is also of the A type. So therefore we can simply say that here A to A type of packing will take place in the case of square close packing of the two-dimensional packing. So here hexagonal close packed of two-dimensional packing, if you take a particular layer, first layer, this is first sphere, this is second sphere, this is third sphere, fourth, fifth, sixth and so on. Now what we are noticing here is, if this is the first layer, this is the first layer. In the first layer, you are finding that all the spheres are coming in contact with one another. one to other in the horizontal plane. Now when you go to the second layer, when you are going to the second layer, the arrangement is slightly different. What you're trying to do is, you can see certain amount of depressions here. See, these are the depressions. The point of contact between the two spheres is called the depression point. I mean to say, this is a kind of void point. These are the depressions. I am trying to thicken that particular area. You are able to see that here there is a kind of the point of contact. You can see this is the kind of depression taking place. At those depressions, what we can do is, you take one sphere and you place over that depression here. Here you place one sphere, then you place another sphere like this. Then you place another sphere like this. Then you place another sphere like this, another sphere like this. And you continue. Take another sphere like this, and here also you can take another sphere like this. Now you are able to notice that the second sphere, the first layer spheres are not the same as the second layer spheres. So the first layer is designated as A, second layer is designated as B. A and B are not same. Again, if you take the third layer is a repetition of the first layer. Third layer means, again what I am doing here, again I am placing one sphere, again between the depressions of the two spheres. Again we can find that this is a kind of arrangement taking place. Again here the kind of arrangement, again here this is a kind of arrangement. This is the kind of arrangement taking place. So from this, it is very clear that this is sort of repetition. Again, this is resembling, the third layer is resembling the first layer. This is again third layer. So third layer repeats the first layer. So again you find that the kind of repetition takes place. This is B and this is A. So AB, so here it is very clear that AB of AB type of arrangement takes place, because the second layer spheres are different from the first layer spheres. So in the second layer you take one reference sphere. If this is the reference sphere, then you try to identify how many number of spheres are coming in contact. So this is 1, this is 2, this is 3, this is 4, this is 5 and this is 6. This is the reference sphere. You can take any reference sphere. Even if you take this as the reference sphere, here also again same thing, 2, 3, 4, 5 and this is 6. Okay, so this is the reference sphere I would like to highlight. This X represents the reference sphere. So based on that reference sphere, we can predict the coordination number of a given sphere with respect to other neighboring spheres. So therefore, in the case of HCP, two-dimensional packing of HCP, we can outright say that 6, that means one sphere is surrounded by 6 more spheres. One sphere is coming in contact with the 6 spheres. 6 spheres. So therefore the coordination number is 6. So as of now we have completed one dimension and two dimension. In two dimension we have studied about the square close packing of the crystal lattice, and in two dimension again hexagonal close packing of the two dimensional packing. We are calling it as hexagonal packing because you find that this is a hexagonal plane actually. Why we are calling it as hexagonal packing? It is hexagonal. We are calling it as hexagonal close packing. Why we call it as hexagonal close packing? We are calling it as hexagonal close packing. It is something like, if you take a hexagonal plane, something like, suppose if I am taking like this is one hexagon. If I am taking this as a hexagon, then you try to mark 6 spheres. Here you mark one sphere. Here also you mark one sphere. Here you mark one sphere. Here you mark one sphere. Here you mark one sphere, and here also you mark one sphere. So in between, this is the reference sphere. So I am taking one more sphere. So I join all of them like this. So this is a hexagon. It's a kind of hexagon. Actually, this is the face of the hexagon. A sphere is there in the face of hexagon. and these are the corners. These are the corners of hexagon, and because it is hexagon, here what we are noticing here is like because there are 6 spheres at the 6 corners of the hexagon, each sphere at the hexagon, the contribution, that is contribution of each corner. Actually we call this as HCP because HCP is nothing but hexagonal closed packing. In the hexagonal closed packing, what you are noticing is it has a hexagonal plane, wherein which in this hexagon there are 6 corners of the spheres. This is of the same layer. If you take a same layer of the hexagonal closed packing, in the same layer you are finding that the center of the hexagon we have one face, that is nothing but called as face of the hexagon, and the surroundings of the face in the hexagonal plane we have 6 spheres in the 6 corners. So by using little bit of common sense, because it's a hexagonal plane, in the hexagonal plane the contribution made by each corner of the hexagon is around 1 by 6. In the cubic cell the contribution of each corner is 1 by 8, but in the hexagon, based on the hexagonal plane, the contribution made by each corner is 1 by 6, and similarly the contribution made by each face in the hexagon is again 1 by 2. So based on this we can easily understand that. Now that means here if you carefully observe this hexagon, this face, it is coming in contact with the 6 spheres within the same layer. This face is coming in contact with 6 spheres, so therefore we can say that its coordination number is 6. So from the diagram also it is very clear that from the 3D picture of this hexagonal closed packing also, reference sphere is coming in contact with the 6 spheres, so the coordination number is 6. So the next part of the discussion is, that is third bit, that is 3-dimensional packing. In 3-dimensional packing we have to study about the first one, that is we can take hexagonal. Again here we have hexagonal closed packing, and we have second one, face center cube. This face center cube is also called as cubic closed packed, which is simply called as, otherwise we sometimes call it as cubic. So here FCC means face center cubic, face center cubic. CCP means it is cubic close packed, cubic close packed. And here what we need to understand here is, suppose if I am taking the first case, take the first case, that is hexagonal close packing, that is I am going with HCP, hexagonal close packing of HCP, hexagonal close packed crystal lattice of 3D packing, of 3D packing, hexagonal close packed structure of 3D packing. So here in the case of hexagonal close packing, HCP of 3D packing, the arrangement is again AB type of arrangement occurs. Next is packing fraction percentage is equal to, packing fraction percentage is equal to 74%, and voids fraction is 26%. Here the coordination number of the hexagonal close packed in 3D packing is 12. How it is 3D packing is 12? Because we find that this 12, the coordination number is 12, because what we are noticing here is, in the same layer 6 spheres comes in contact. Let me put it in this way: same layer 6 spheres comes in contact, same layers 6 spheres comes in contact, then you find that comma, then above layer or top layer 3 spheres, and bottom layer another 3 spheres. So here this is the analysis we have to make. If the HCP, if the hexagonal close pack is having coordination number 12, means you find that in the same layer it comes in contact with 6 spheres, in the top layer the face of the hexagonal plane is going to coming in contact with 3 spheres, and the bottom layer another 3 spheres. So for this, if I am going to give you a diagram, let us prove the coordination number 12 in the case of hexagonal closed pack of 3D packing. So what I need to do here is like I am going like this. This is the sphere at one corner, then I am going to take another sphere over here, another sphere over here, then another sphere over here. Okay, fine. So like okay, so one sphere I am going to take it over here, and one more sphere I am taking over here. Okay, fine. And in between we have a face. Okay, so now I am trying to join all the spheres like this. Trying to join all the spheres like this. Okay, I have joined. That means one layer has been completed. Now go to the, now suppose if I am going to take drop one perpendicular in such a way that it covers the maximum distance. So here also we place one sphere, then I think we can take, yeah, because this is in the above plane, so drop one more sphere and you just stop over here, and here this is one more sphere, then here also you do the same thing, almost bring it to the same position, and here you bring it to the same position like this. Both of them should be in the same plane. Now you can take one sphere, you can just put it over here like this, something like this, and here I am going to stop it over here. Now make it a little bit bigger, these spheres. Yeah, so and now you can join them. So I am just joining it over here like something like this. Okay, fine. So slight difference is coming over here. Yeah, so here also we have one face, here also we have face, and what we are noticing here is in between we have 3 body centers. So that 3 body centers also I am going to make a note here. So this is one body center, this is another body center, and this is another body center. These are the 3 body centers. So here what is happening is like if you take this is the first layer, so consider this first layer as A, and this is the second layer. So I'll go from here, this is second layer, this is the second layer, and consider this as the layer, second layer, which is different from the first layer, and again consider this as the third layer. If this is the third layer, again it's a repetition of the first layer, because you can see very clearly if the third layer is a sort of repetition of the first, because here you have a hexagonal plane with 6 spheres and one face. So here also hexagonal place with 6 spheres at the 6 corners and one face. So this is again a sort of repetition. So when we are speaking about the coordination number, what we have to understand here is, so likewise suppose if I am going to take, if I consider one more bottom layer, again you find that 3 body centers will arise here. For our convenience, what I am doing here is I am trying to take one more 3 body center spheres I am trying to take here. So that means if you are taking this as a reference sphere, for example in the same layer, because we are saying that the coordination number is 12, in the coordination number 12 we are saying that in the same layer, that is in the same layer it has 6 spheres, the top layer it has 3 spheres, and the bottom layer it has another 3 spheres. In the same layer 6 spheres means if this is the face of the hexagon, in the face of the hexagon you have 6 corners, that means for this face 6 spheres are coming in contact. When it is coming in contact, for our convenience I can even just connect it like this. These 6 spheres are coming in contact. These 6 spheres are coming in contact, and at the top layer you are finding that because this is a face, yes, this face will come in contact with 3 body centers. So I am connecting these 3 also. That means already 9 spheres have coming in contact with the face of the hexagon. Likewise, if you go to the bottom again, you find that if this is the top layer, this will be the bottom layer. So again, the face will come in contact with another 3 layers. So therefore, from this illustrious, diagrammatic view of the hexagonal closed pack, it is very clear that the coordination number of the hexagonal plane, if it is 12, the same layer it has 6 spheres. Yes, this is the same layer, it has 6 spheres at the 6 corners. Top layer, it has 3 spheres. Top layer means if you consider this as the top layer, it has 3 spheres at the body center. All 3 spheres are coming in contact with the faces. Another 3 spheres at the bottom. The 3 spheres, again 3 body centers at the bottom. Top layer, bottom layer, same layer. So total it is going to become, the coordination number is going to become 12. So this is how we have to understand the hexagonal closed packing in the case of 3D packing. And what are the examples we can take? What are the examples we can take for the hexagonal closed packing in the 3D packing of the crystal lattice? So here if you go to the examples of hexagonal closed packing, HCP of 3D packing, lithium, beryllium, calcium, helium, chromium, molybdenum, cerium, zirconium, osmium and ruthenium. So what we are noticing here is there is only one element which belongs to, that is F block, cerium. It belongs to F block, but if you take zirconium, osmium, ruthenium, chromium and manganese, molybdenum, these 5 elements belongs to D block. So you find that chromium, molybdenum, zirconium, osmium, ruthenium are the D block elements, and cerium is the only element which is F block element, and lithium, beryllium, calcium and of course helium. So these belongs to, that is lithium, beryllium and calcium. If you take, these are S block, and the helium belongs to noble gas element, that is the P block, that is 18th group P block element. So this is P block. Of course, if you write the electronic configuration, it has to come to S block only, but still it is considered as P block because it is kept in the 0 group, that is 18th group of the periodic table. And the rest of the elements, chromium, molybdenum, zirconium, osmium and ruthenium, they comes under the D block elements. So it is just logical understanding or logical memorizing of the different elements of S block, P block and D block and F block. We can consider that the examples can be remembered, and we have to understand that from these examples, from this group of examples, it is clear that the crystalline solids, the crystal solids, the HCP structures are possible for all blocks of elements S, P, D and F. So specifically we have to remember few of the examples in the logical manner like this. So here if you go for the hexagonal closed packing, if you continue with the diagram, this here we can consider, if these are the 2 spheres, the distance between the 2 spheres is given by, that is 2r. The distance between the 2 spheres is given by 2r, which is equal to edge length. So A is equal to 2r, and this is the height, total height of the hexagonal closed packed structure. This is the height of the 2 hexagonal planes. H is the height of the hexagonal planes, and if you take the 3-dimensional viewing of the hexagonal plane, something like this you can take. Suppose if you are taking, first I am going to take 3 spheres like this, then I can take here 3 spheres you can take. So like we can take, so here if you take the 3-dimensional view of the the frontal view of the hexagonal closed packing, you can see one hexagonal plane 1, 2, 3, 4, 5, 6 with middle one face, again 3 body centers, and here again one hexagonal plane with 6 corners and 1 face. So from this it is very clear that here it has the repentance of AB type of arrangement is taking place. Okay, 3-dimensional arrangement. This is 3-dimensional arrangement between 2 layers. Repentance. It is very clear that there are 3 layers. The first layer, second layer, the third layer is a repeat of first layer. A is repeating B here. A is again repeating B, then again B will repeat another B like this. It continues. So therefore AB type of arrangement takes place in the hexagonal closed packing. So here if you look at this diagram, this illustration, this is face centered cube in 3D packing. Face centered cube in 3D packing, if you take some important conclusions, what are the conclusions we can make here? From the diagram we are able to understand that FCC is nothing but that is face center cube, face center cube. From the diagram we are able to understand that this face center cube is also called cubic closed packed structure, which is nothing but CCP, or sometimes we also call this as simply cubic. We call this as cubic. Here the coordination number is 12. When I am saying coordination number as 12, same layer, again just like HCP, same layer, that is 6 pairs, same layer 6 pairs it has. Then bottom layer 3 spheres coming in contact, and again top layer another 3 spheres coming in contact. So this speaks about the coordination number. How we can justify? You take any reference layer. Suppose if I am taking here, this is the fourth layer, or you can take the first layer or any layer. You go for the fourth layer. If you take the fourth layer, this A is the fourth, third, second, first. So if you go for the fourth layer, the C layer is going to become the bottom layer, and the next layer again it's a repetitive layer. Again you find that in the same layer for the given sphere, if this is the face, you find that it is coming in contact with the 6 spheres. Bottom layer it is coming in contact with another 3 spheres, and again in the topmost layer it will come in contact with another 3 spheres. So therefore the coordination number is justified. And because you are finding that 3 different layers are there in the FCC, you find that the fourth layer is a repetition of the first layer, because all 3 layers are different, they are different arrangements. So therefore here the arrangement of spheres follows the order ABC type of arrangement. And if you go for packing fraction, percentage, it is 74%, and voids fraction, if you take just like HCP, which is equal to 26%. Now take some examples. What are the examples where we can study examples of FCC in 3-dimensional structure? What are the examples we can take? So if you look into the examples, copper, silver, gold, platinum, copper, Cu, silver, Ag, Au, gold, Pt, platinum, all these are said to possess the structure of the face centered cube of 3-dimensional packing, and these are all, that is malleable and ductile. These are all malleable and ductile, and you can take also aluminium, chromium, cobalt, copper, silver and lead. Of course here we have taken copper, so no need of copper here, striking of copper. Then take manganese, nickel, calcium, strontium, platinum, and neon, argon, krypton and xenon. Except helium, rest of all noble gases, they show the face centered structure, except noble gases. Remaining except helium, except helium, remaining all noble gases, they show the FCC structure. Helium is an exception. Neon, argon, krypton, xenon, they show FCC structure of 3-dimensional packing. So the next part of the discussion here is, that is concept of voids. If you go for voids are also called, that is gaps. Gaps are also called interstices. interstices or simply holes. So when you say holes, so I'll put it in this way. Voids conveniently can be called as gaps or simply holes. So suppose if I am taking voids, types of voids, if you're taking types of voids, here we have trigonal voids, we have tetrahedral voids, and we have, that is, octahedral voids. Number of spheres involved in the trigonal voids are 3 spheres. In tetrahedral voids, they involve 4 spheres, and octahedral voids involve 6 spheres, and they require minimum 2 layers at least. In all the cases it requires minimum 2 layers, but if you take particularly if you take, we can create a trigonal void. Trigonal voids can be created in the same plane itself, in one single plane. It can require single plane of the same layer, Here it requires 2 layers, and here also it requires 2 layers. So what we are noticing here is, for example, here if you take trigonal voids, number of spheres are 3. So like if you go for trigonal voids, let the trigonal voids be represented by T dash of V are the trigonal voids. Tetrahedral voids is TV, and octahedral voids are O of V. So if you're going for, that is T dash of V, that's nothing but trigonal voids. Here we have 3 spheres, so first sphere, second sphere, and third sphere. So you have, this is nothing but, you can see this gap, this is nothing but a void or a hole involving 3 spheres, 1, 2, 3. So it is planar in nature. So actually here if you take, that is small r by capital R is equal to 0.155. If you take, then small r is equal to 0.155 into capital R. So here small r is taken as radius of the trigonal void, and capital R is the radius of sphere, is the condition. So that is nothing but about the, we are speaking about the trigonal void. Now if you go for tetrahedral voids and octahedral voids, this tetrahedral voids and octahedral voids can be identified as, the topic is, that is identification of tetrahedral and octahedral. Identification of tetrahedral and octahedral voids. So usually what we do is, we can identify the tetrahedral as well as the octahedral voids in, that is in 2-dimensional packing of crystals. So you find that we have 2 layers, it involves 2 layers. So we have to understand how these two layers operates, such that we can identify both the tetrahedral as well as octahedral voids.